honestly, because if you are, you're going to miss some extremely interesting exoplanet research that I've done over the past 2 years, and my presentation today will be a combined presentation over a few presentations that I've done over the past few years. And this first part of it is called The Search and Discovery of Coral 29, Photometry of Transiting Extrasolar Planets Using the Coral and Fox Telescopes. So just so you know, I'm not looking at my text messages. It's for flipping the slides. I don't get text messages because I don't have any friends. Well, I spend all my time researching exoplanets because they're fascinating. An exoplanet is any planet that's revolving around a star that isn't our own sun, so not Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, or Neptune. These planets are many light years away and are very difficult to detect because they're so far away. So the first exoplanet was discovered in 1992, revolving around a pulsar, which is kind of a weird variant of star. So the first exoplanet revolving around a normal main sequence star, like our own sun, was discovered in 1995 around a star in the constellation of Pegasus, Pegasi 51. And since then, many more exoplanets have been discovered, 1,782 to be exact, that are confirmed right now, but more are being found every day. There are various different methods of discovering extrasolar planets. The most obvious one of which is just simply taking a picture of the planet. But that's very not simple because the star's brightness that the planet's revolving around blocks out any chance you have of directly imaging the star unless you take various measures to direct image the exoplanet in question. So this is an image from the Hubble Space Telescope that blocked out the disk of the star in order to directly image a planet which you can't even see on the screen. So it's very difficult to directly image planets. So most planets are discovered using indirect methods, such as the Doppler shift method, which involves looking at the redshift or the blue shift of the star as it rotates, as it wobbles towards and away from Earth, due to the fact that the exoplanet revolving around that star pushes or pulls that star towards or away from Earth. And by measuring the redshift or blue shift of the star in question, you can discover whether there's an exoplanet revolving around it. There's a bunch of other different new methods of discovering extrasolar planets, such as gravitational microlensing, which involves the very complicated process of looking at a star that's behind the star that you're looking at, and by measuring the way gravity affects the light from that background star, and by looking at the bending of the light from the background star as it bends around the foreground star, you can discover small objects around that foreground star. If you're very confused, I am too. So that's why I used a different method called exoplanet transits, which involves looking at the brightness of the star you think has an exoplanet around it, and by measuring that brightness over time, and detecting a dip in the brightness, as you can see from this animation here, the star's brightness goes down as the planet crosses in between the observer, you, and the star that you're looking at. And if that dip is regular, it happens once every month or so, or 3 days maybe, you can tell that something is revolving around that star, blocking out some of the light. Okay, so what I wanted to do with my project was find a new extrasolar planet using this transit method. And that's a very difficult task because not a lot of extrasolar planets have been discovered, but that was my goal for this project. So I was very fortunate to be able to work with scientists from the European Space Agency because they have a special telescope called the Coral, or Convection, Rotation, and Planetary Transits Telescope. And this is a space telescope that scans the sky with a low-resolution camera and a wide field of view, looking for very minute fluctuations in light intensity of fields of stars. So when it discovers a field of stars that appear to dip in brightness, it makes a note of that field and sends it to scientists in Europe. And because this Coro telescope does not have the resolution, the spatial resolution, in order to distinguish different stars from each other in a large field, you have to follow up observations of the Coro telescope with a larger land-based telescope with better spatial resolution and a higher resolution camera. And for this, I was happy to work with people from UH Manoa and the Institute for Astronomy, and also people on Maui, like my mentor, Dr. J.D. Armstrong, and he hooked me up with the Fox Telescope Project, which is a project that allows students to use a large telescope on Maui and a twin sister telescope in New South Wales, Australia, to study the sky and do research projects with them. And these are world-class 2.2 meter telescopes, so they're very big and can be used to do extremely good science. So with my contact at the European Space Agency, I received 3 different fields that were candidates to have an extrasolar planet in them. And most of these candidate fields don't have extrasolar planets in them. It's like a false positive. They thought it might have an extrasolar planet, but it actually didn't. But I got 3 of them, so my chances were better. I got 2 candidate star fields near the constellation of Ophiuchus, and I looked at 1 candidate star field in the constellation of Orion, which you all saw last night on top of Mauna Kea. And this is my table of observations that I took using the Fox Telescope North and the Fox Telescope South. So on May 27th and September 7th, 2012, I took data with the Fox Telescope South of the field near Ophiuchus. And on September 14th in 2013, I took another field, another data of another field near the constellation of Ophiuchus. And on December 7th, 2013, I took data with Fox Telescope North of the field near Orion. After I got these images from the Fox Telescope North or Fox Telescope South, they're essentially time-lapse images. So I loaded them into a program called MIRA, or Micro Image Reduction and Analysis Software, and that allowed me to stack those time-lapse images on top of each other, and also get the exact brightnesses of each star in the field. So once I had those numbers, I would be able to graph those numbers over time to get the star's brightness over time graph. And if I saw dips in that graph, I could infer that there's something passing in front of the star, and if those dips were regular, I could say that that was an extrasolar planet. This is my first set of data that I got on May 27th in 2012 of a field near the constellation of Ophiuchus. And this one star in that field here, of this graph here, with time on the x-axis and brightness on the y-axis, it appeared to dip in the middle a little bit as compared to other stars in the field that appear just flat. So I was very excited to see that dip, even though it doesn't look like a perfect transit, because obviously observing conditions are never perfect. But I sent that data to Coro scientists in Europe, and they were also very excited to see a dip in one of the stars in that field, so I continued looking at it, and they continued looking at it with European telescopes. And this is a second set of data I got from that same field, and this graph is of the same star. However, you can see that it doesn't look like a dip, it looks like a hump. But after confirmation with the European Space Agency, we decided that this hump is because we got the tail end of the transit, and we didn't start, I didn't start the observation in time in order to get the entire transit. But since the European Space Agency did some of their own observations of this star field, we decided that this is actually an extrasolar planet, judging by the regularity of the dips in the light curve of the star. So I am very happy to be part of a team that discovered a new extrasolar planet called Coro 29. And this hump discovery is also significant to the discovery of Coro 29, because it wasn't because I entered the timing wrong on the telescope or anything like that. It's because that what we thought the planet's period was off by an hour and a half. So this was able to correct that. So not only did I help do the preliminary observations of Core 29, I also was able to correct the ephemeris, or position of the planet in time around its star, and that's a very important discovery as well. In this same project, I also looked at 2 other star fields. This one I looked at in the constellation of Ophiuchus is another one that appeared to have one star that dipped in the middle, but it's not clear exactly if that's actually an exoplanet dip, so I have to do more research on this star in the future. And I also took another set of data of a star field, and I looked at all the stars in the field, but none of those stars appear to have extrasolar planet transits, or any transit whatsoever. And this is just an example graph of one of the stars in that field. So in conclusion, I helped to discover a new extrasolar planet, Core 29b, which is a hot Jupiter planet, which means it's a Jupiter-sized-ish planet. It's 0.7 Jupiter masses, and it's right next to the star, which makes it hot. So it has a period of only 2.9 days, which is far inside the orbit of Mercury. I also looked at other star fields, one of which, the one I looked at December 7th, near the constellation of Ophiuchus. It might have had a transit dip, but I'm not sure. And the other star field I looked at definitely had no result. For future research, after I finish this project, I wanted to look at transit abnormalities, which are things that could change the shape of the transit, such as exoplanet tails, which is when the exoplanet is so close to the star that parts of it are melting off, blocking out some of the light even after the planet is done transiting, and other things like limb darkening and bow shocks, which I can talk later about if you want. I also wanted to look for exoplanet atmospheres. And the way you do this, or the way I decided to do this, was look at the star in question and take transits of the star in question, transit light curves, using 2 different color filters, one red filter and one blue filter. And if the planet has an atmosphere, like our own Earth, that blocks out and scatters red light, the planet would appear bigger in the scatters blue light, sorry. It lets through red light and scatters blue light. It would appear bigger in the blue filter than it would in the red filter. So I decided to take transit data of stars using blue and red filters, and at a summer camp called High Star, which I went to a couple weeks ago with Lily Jenkins and a lot of other really smart people, I was able to take data of these exoplanets using these 2 filters. And these are my teammates, Cameron Chaffee, Connor Lay, Milani Neal, and Rochelle Kabedek. And there, we looked at 2 stars, TRES-3 and GJ3470, which are both confirmed to already have large exoplanets revolving around them. So we figured that these would both be good candidates to have exoplanet atmospheres on the exoplanets revolving around these stars. So these are really nice light curves. And we got light curve data with both the red filter and the blue filter. So the red dots are in the red filter and the blue dots on the blue filter. And this is the data from my planet GJ3470 with, again, time on the x-axis and brightness on the y-axis. And you can see, even though we only got a half transit in the blue because the cloud was in the way, you could see that the blue looks slightly deeper than the red. And again, in this next light curve, again, blue looks slightly deeper than the red of this light curve of a star called TRES-3b. However, this is still not conclusive of an exoplanet atmosphere, because you can see our error bars in both of these observations overlapped. So if the error was to the extreme, with red being low and blue being high, then there's still no result. So there's nothing that we can say about atmospheres on these planets quite yet. I also wanted to do spectroscopy of exoplanet atmospheres, and I was again fortunate to go to another summer camp on top of Kitt Peak in Arizona, where I was able to use a telescope on top of Kitt Peak called the WIN 3.5 meter telescope, which is a super big, ultra-professional telescope that's new on top of Kitt Peak. And it has a multi-object spectrometer that allows you to take spectra of multiple objects in a field. And using this, I took tried to take spectra of an exoplanet atmosphere as it revolved around its star. That exoplanet was again a TRES 3b. And the multi-spectrometer was used to take spectra data of other objects in that field to cancel out any atmospheric noise that the atmosphere produced on the exoplanet data. So we took the spectra of a star that we knew the composition of, and we canceled out the atmospheric noise in that, and we canceled out that same atmospheric noise in our exoplanet data. However, this data is still being analyzed because it's very complicated. This is supposed to go before that other slide. But this is my conclusions for that exoplanet atmosphere project that I did at High Stars a few weeks ago. Again, it's not confirmation of an exoplanet atmosphere. And so that concludes my presentation for today. I'd like to acknowledge a few people like my mentor, Dr. J.D. Armstrong, and Ms. Kataoka, the High Star Director, as well as all the organizers of this amazing summit that I'm in right now, and of course all of the students. And are there any questions?
What do you use to make sure that the changes in intensity that you're looking at aren't just temporary absorptions in the atmosphere? Is there a control or something that you use to ensure that?
There's a couple methods that are used to ensure that your data is good. One of them is in this program that I explained before called Myra. It is possible to, all these red stars are stars that I'm looking for exoplanets on, but that yellow star is a star that I know is a constant star, so it's not varying in any way, and a constant along with the shifts in the atmosphere. And so what you do to normalize your data for the exoplanet stars is you divide the exoplanet star brightness by that check star brightness, and what you're graphing here is just the ratio of that brightness to the check star brightness. And when your star in question brightness changes and your check star brightness doesn't change, that's how you know that it's shifting and not the atmosphere. And also, just because you have one set of data that has a dip in it doesn't mean in any way that you have an extrasolar planet. You need tons of dips to confirm an extrasolar planet. Each different method of looking at planets have different advantages for doing just that, calculating things like mass and size. Yeah, and with the transit, you can look at the amount of light that is blocked out. But you can look at the amount of light that's blocked out, and from that, and the amount of wiggle it gets from the Doppler shift, you can tell the distance from the star using the Doppler shift method. And then from that, well, the mass of the star as well, using that Doppler shift method. And then from the transit method, you can discover the size based on the amount of dip you get. So normally exoplanets get between 0.001% to 0.01%, depending on the size and proximity to the star in question. So you just look at the amount of dip you get in the exoplanet. So the deeper it is, either the closer it is or the bigger the planet is. Yeah. Yes?
What is known about the Kourou 29 star?
The star itself? Ooh, I have a paper that is being written. In somewhere. And it is a oblated star, which is interesting, and it's also a, I believe it's an M-class oblated star, so it's bulging. That's what's known about that star. I'm sure there's more written in this paper, but it's not done yet. So, oh, and I get to be a co-author on a paper that's going to be published in Astronomy and Astrophysics, so that's nice.
Yeah.